Greetings to you. We are going to continue our discussion on the infrared spectroscopy, and we were discussing the electromagnetic radiation, that is the interaction of electromagnetic radiation with matter. I had shown you the spectrum of the electromagnetic radiation, that it contained gamma rays, cosmic rays, X rays, ultraviolet rays, and then soft X rays, UV, visible IR, near infrared, infrared, microwave, far infrared, and all those things. I had shown you this slide in my last class. Look at this slide now. So, what I had told you was this is the whole spectrum. It has a frequency range from 10 raised to 24 to several kilo 10 raised to 0, several frequencies 10 raised to, and then it has a wavelength, that is a range from 10 raised to minus 16 to several kilometers of the amplitude, and I had shown you that the visible spectrum is a very small portion of the total spectrum which we perceive personally as human beings, and I had explained to you about this earlier. Okay. Then I had explained to you that the visible range can further be divided into several areas, and the transmitted color and complementary hues I had explained. The transmitted color is what comes out, and complementary hue is what the material looks to you as an observer. That is, it retains all the other absorbed colors. Okay. So, we noted that there are no sharp differences in the color at any wavelength, etcetera, etcetera. And then I had explained to you how we get an absorption peak if we use a molecule for the interaction of electromagnetic radiation, which will end up transitions of the electrons from electronic, vibrational and rotational energy levels. And I had also explained to you how we get a peak instead of a single sharp line, especially in the UV, visible and IR regions. Okay. And then I had explained to you that monoatomic substances normally exist in gaseous state and absorb radiation only through an increase in the electronic energy. There are no vibrational or rotational energy levels in monoatomic substances. These electronic energy levels are also quantized and appear in various subshells. I had shown you this figure, and these figures are arranged according to their increasing energy, that is 1s, 2s, 2p, 3s, 3p, and then 4s, 3d, 4s, etcetera, etcetera, and these are the electronic energy levels. Subsequently, we had discussed about the polyatomic molecules, where electronic transitions involve molecular orbital changes requiring energy in the ultraviolet region and visible region, etcetera, and these are far more complex because they involve vibrational and rotational energy levels also. So, the total energy may be considered as a sum of the contributions of all the energy, all the states of energy of a molecule whenever it is exposed to electromagnetic radiations. So, for each electronic energy state of the molecule, there exist several possible vibrational state, and for each vibrational state there exist several rotational energy levels. I had explained to you, they are giving you an analogy of kicking a football on the staircase to land on the first floor, second floor, etcetera, and that is the best analogy available as of now. So, the electronic transitions in organic molecules are also characterized by the promotion of electrons from the bonding and non-bonding molecular orbitals to excited energy state. That is, the excitation is always into antibonding orbitals, okay, from the bonding orbitals. So, the bonding orbitals are designated as sigma and pi orbitals. Then there are other electrons in a molecule where the electrons are not bound, but they are free. They are known as non-bonding electrons, and they occupy certain energy level in the molecular bonding hierarchy. So, these non-bonding electrons are quite often found in compounds containing oxygen, nitrogen, fluorine, sulfur, etc. So, many molecules contain these compounds, these elements, and you can see that aldehydes, ketones, they all contain oxygen, water contains oxygen, ammonia contains nitrogen, amines contain nitrogen, all these, every element, oxygen, nitrogen, sulfur or halogens or other anions would be having these non-bonding electrons. So, especially when such molecules are subjected to electronic excitation, these electrons also get affected, they absorb energy and go to the higher energy states described by antibonding orbitals. So, the generalized shapes of the orbitals also I had shown you in my last class, and then I had shown you that the stability or dissociation occurs, stability gets affected, dissociation occurs if I submit the electrons to very high energy levels that would require crossing the anti-bonding energy levels also. So, the electronic transitions possible in ultraviolet regions we had defined as sigma to sigma star, sigma to pi star and pi to pi star. So, for every bonding there is sigma star and pi star, but for n electrons, that is compounds containing oxygen, nitrogen, sulfur, etc., there are no anti-bonding n orbitals, only sigma star and pi star. So, N2, if I excite the electrons in the non-bonded electrons like oxygen, nitrogen, etc., those electrons, where will they end up? They end up either from N to sigma star, same existing levels, or N to pi star. So, both these possibilities are there, but there are no N to N star antibonding orbitals. So, what happens? Basically, we are talking about sigma to sigma star and then pi to pi star, N to sigma star and sigma to N to pi star. So, 4 excitations, especially in the bonding and antibonding orbitals. So, suppose I have only sigma bonds. All compounds are saturated hydrocarbons. There are no pi bonds. Okay. So, only single bonds between each atom, whether it is carbon carbon or carbon hydrogen carbon, that is it basically. Hydrocarbons means compounds containing only carbon and hydrogen. So, there are only single bonds in a set of series, then I can expect only sigma to sigma star transitions, because there are no pi electrons and pi star energy may be there, but it is not defined, because they are all containing only sigma bonding. Similarly, alcohols contain oxygen, and sometimes they, if you look at the structure of aldehydes or ketones, I have pi bonds. Acetic acid or any carboxylic acids have got a functional group of C double bond O and OH, that is the functional group. So, COOH is a compound having a pi bond and non-bonding electrons also. Similarly, CHO, aldehyde, ketones and many other compounds. So, the transitions, energy required for the transitions from sigma to sigma star would be much more than they are in the from pi to pi star or n to pi star. N to sigma star also the energy will be required. So, the highest energy level would be for sigma to sigma star. So, the electronic excitation energy levels involve large amount of energy ranging from 35.71 kilocalories in the visible region to several hundreds kilocalories in the far ultraviolet region. So, each electronic level associated with vibrational modes, but maximum population would be at mu is equal to 0, that is vibrational energy level 0, and consequently absorption arising out of V is equal to 0 would be having maximum population of the electrons. Okay. So, whenever I have an molecule, a group of molecules present in the ground state level, maximum population of the electrons would be at V is equal to 0. And such energy transitions starting from V is equal to 0 to V is equal to 1 next etcetera energy levels, they would be maximum also. So, the intensity of the absorption peak would be maximum starting from V is equal to 0 to next higher energy level. But it does not mean that there are no other vibrational energy levels where electrons are not populated. They also occur to some extent. So, what happens is in the end we see a sort of broad absorption band instead of a sharp absorption peak. So, I had explained to you, look at the slide now, the sigma to sigma star transitions are basically very energetic. This I had explained to you because you need several kilocalories, from 35 kilocalories to several hundred kilocalories for excitation from sigma to sigma star. So, they are called as very energetic excitation states. They are found only below 200 nano. If more energy is required, then the absorption peak would be appearing only at very low wavelength. That means that is how the whole system of electromagnetic radiation works. Higher the wavelength, low is the energy. Lower the wavelength, high is the energy. So, because sigma to sigma star transitions are very high energy levels, the excitation absorption peaks should appear at low wavelength range, okay, and higher frequency range also. Both mean the same essentially. So, spectroscopy is basically the measurement of and interpretation of electromagnetic radiation passing through the system containing molecules etcetera, molecules, water, solvents, whatever are the other things that contain in the that are contained in the matrix. So, absorption, emission, reflection, reflection, everything will occur when electromagnetic radiation is interacting with the molecules or chemical species. So, all these processes are associated with energy changes, and the energy states of the species or modification of its direction or intensity. So, every electronic transition is associated with the changes in the electronic state, electronic energy and the direction also. So, what is electromagnetic radiation? That is considered as a wave which carries energy from one location to the another at a finite velocity that we have already seen. It is velocity of light, that is 3 into 10 raised to 10 irrespective of the wavelength or frequency. So, as the name suggests, electromagnetic radiation has two components. Okay. One is electric field and another is magnetic field, which are perpendicular to each other. I had shown you this figure also earlier, and one is perpendicular to another, that is the red one appears should appear to you as an observer. If you are looking at an electromagnetic radiation, it appears as a peak like this, whereas the magnetic field will appear as a perpendicular wave. So, the direction is very important as far as electromagnetic radiation. That is what I had shown you in this figure. It has got x axis, it has got y axis, and the direction of propagation of the electromagnetic radiation I have shown here. It is in this direction, but the electric field is like this, and then it goes like this, it goes like this, etc., whereas magnetic field will go perpendicular to that. So, many properties of the electromagnetic radiations are considered as discrete classical discrete energy levels, particle energy, discrete energy particles is one thing. Another thing is we can also consider it as a wave. So, conveniently we can describe the properties of both, that means any electromagnetic radiation as a classical sinusoidal wave, which I shown you earlier. So, it has got characteristic wavelength, frequency, velocity and amplitude. So, electromagnetic radiation passing through vacuum also will contain all these components, even if it is in vacuum, unlike sound waves. Sound waves cannot travel through the vacuum. So, some properties of the electromagnetic radiation, they are both described best as a number of streaming particles instead of waves. That means, if a light is, if you are seeing a light coming from a bulb through a battery, you will see a straight line, a shining light penetrating the space. Quite often you will see that. Just put on a torch and see how you can see the light coming in a straight line. So, that means all the, if we assume that the photons or the electromagnetic radiation contains number of particles, those particles are moving in a straight line. Actually, it is not a straight line, but the particles which are called as photons, it appears to you as if it is passing through a straight line path. And then the it is, you can consider it as a streaming particles that move from one place to another. So, because electron has got velocity and electromagnetic radiation also has got velocity, it can travel. So, we can consider it as a bundle of energy traveling through the space from one point to another. So, these properties are best described as a number of streaming particles traveling in a wave form, that they are known as corpuscles, that is discrete particles or photons. More popularly they are known as photons, but corpuscular theory is a typical word used in several physics textbooks, etc., which does not which means it is particulate theory. So, according to Heisenberg's principle, here we will invoke that it is impossible to measure the wave and particle properties of a photon simultaneously. You cannot measure simultaneously. Assume that a wave is moving like this at a given point. You cannot determine the particle, where it is, and at the same time you cannot determine how is the wave moving. There will be certain amount of uncertainty or error if you want to measure both. This is a very important concept, a quantum mechanical concept. What it says is you cannot measure them simultaneously, or if you measure simultaneously you cannot measure them exactly. So, it is convenient for us to imagine photons as particles having specific amount of energy radiating from a source, just like I was explaining to you that if you consider a battery torch cell, you can see that it is everyday battery. You must have seen so many torches, LED batteries, keychain, or most of them appear as if a bright light is going through a straight line, cutting the darkness. So, from a source, the specific amount of energy radiating from a source can be characterized by the electromagnetic wave. Okay. So, how do we characterize them? That is again from the properties only. We have to do it only from the properties. So, the properties what we are trying to describe, they would be something like wavelength of the radiation. I can measure that, that is very simple. Lambda can be visualized as a distance between two maxima, which I have shown you earlier, and you can use them either electrical way, you can measure the amplitude or the wavelength either through the electrical field or magnetic field, either way both will be same. So, you can measure the distance between the two maxima either electrical or magnetic component. So, obviously now when you measure the distance, that is amplitude, between the two maxima, it is also characterized by the frequency. You can say you can measure the frequency also. No need for measuring both, because when you measure the frequency, automatically wavelength is fixed. So, the frequency we define as the number of waves in an electromagnetic radiation passing through a fixed point. Now comes the Heisenberg's principle. If the radiation is passing through a fixed point, you can measure its position, but not the velocity. There will be certain amount of error. So, when a photon passes a particular region of space, the electric and magnetic fields oscillate with the frequency, they get disturbed a little bit. So, only when they get disturbed, it is difficult to measure the wavelength, amplitude. So, the only measure of frequency of an only measure of electromagnetic radiation is the frequency. Frequency does not alter much. So, it is truly the characteristic of a particular radiation. Okay. Now, how do we define it mathematically? Very simple. I define it as A is equal to A0 into sin theta. Any electromagnetic radiation, whether it is cosmic, whether cosmic rays, whether it is gamma rays or ultraviolet rays or X-rays, visible rays, infrared, anything, all waves can be characterized and defined mathematically as a simple expression, that is A is equal to A0 into sin theta. Here we call A is the amplitude at any point, A0 is the peak amplitude, and sin theta is the continuous variable, that is the degree in which the the photon is moving. So, sin theta when it is maximum value, that is 90. So, A would be equal to A0, that is the maxima, and any other degree, its value will be less than 1. So, the wave function can be described something like this, go up and come back, go up, come back. So, it has to be sinusoidal wave, because sin 0 is 0, sin 90 is 1, sin 180 is 0, sin 270 is minus 1, and sin 360 is 0 again, the value of that. So, after 360 again you will be repeating the same cycle, because theta will be where theta can vary only from 0 to 360. So, this is almost a complete description of the wave, electromagnetic wave. I can also write A is equal to A 0 into cosine theta, because the cosine theta also wave is essentially same, except the magnitude. Cosine when theta is 0, when sin theta is 0, the whole thing when theta is 0, sin theta is 0. So, A 0 multiplied by 0 would be 0. That means, when theta is 0, the amplitude of the wave is 0, but when I describe cosine theta, when theta is 0, cosine theta is 1. So, A 0 into 1 would be A 0. That means, the whole electromagnetic radiation, when I am describing either as sin theta or cosine theta, they are differing only by its appearance of maxima and minima rather than its true character. Okay. So, I can also say omega t instead of sin theta. So, omega t is equal to theta, but w is the angular velocity in radians per unit time. This is how we define normally. So, a complete cycle occurs when omega t changes from 0 to 3. This I already explained to you, 0 to 360 degrees. This is called one oscillation or one period, 0 to 360, whether it is sine or cos. Hence, the time over which one complete period occurs is given by the frequency, that is T cycle I have written here. One cycle is nothing but W by 2 pi. What is 2 pi? 2 pi is 360 degrees, or I can say frequency is equal to 1 over T cycle. How many maxima or minima occur, that itself also is given by 2 pi by W. Okay. So, for any wave moving at a constant velocity v, we can write v is equal to v into lambda, frequency. Okay. Velocity is equal to v mu into lambda, where mu is the frequency in microseconds, v is the velocity, and in hertz, that is cycles per second or seconds inverse, and lambda is in meters. Normally, we go for meters, even though we use centimeters, etc., but usually the variation depends upon the convenience of the expression, depends upon the convenience of the waves. Generally, if the wave is long, the amplitude is long, we can say in centimeters or even in meters, like that, or even kilometers if it comes to that. But when it comes to the other side, you cannot say 10 raised to minus 9 centimeters. It looks awkward, even though not wrong. So, we say centimeter, nanometer, picometer, like that, or angstrom units, that also we can say many things. So, the frequency is proportional to the energy of the photon, and that is given by this equation, that is E is equal to h mu. Look at the slide now. Now, I have written here E is equal to h mu. Again, the numbers h means it is 6.62 into 10 raised to 27 ergs when E is expressed in ergs, or it is if you express in joules, then it is 6.63 into 10 raised to minus 34. 10 raised to 7 ergs is 1 joule. So, E is expressed as 1 joule. Okay. Now, sometimes we can define, it is convenient to use wave number instead of the frequency or wavelength or anything, and wave number is denoted here by this expression. E is equal to, instead of writing h c by lambda, we write h c into mu bar. That means, mu bar is equal to 1 by lambda, that is 1 by wavelength. Wave number is nothing but 1 over wavelength, and this is especially true if I am going to measure in infrared spectrum of the compounds, which we are going to studying now. The point is, you can use wave number also, or wavelength, or frequency now to describe the electromagnetic transitions occurring in infrared. Okay. Each system measurement or energy, measurement of the wavelength or energy, normally is associated with a specific spectroscopic technique, which I was explaining to you just now, that if you are using wave number, it is for infrared. Like that, now I have made this table, and here I am putting properties of the electromagnetic radiation as nanometer, and unit is nanometer is a unit for wavelength, and where nanometers are typically used, they are all used in ultraviolet, visible and near infrared, typically used. So, nanometer, angstrom, and 1 angstrom is 10 raised to minus 8 centimeter. So, this is the symbol for angstroms. It is for wavelength, and angstrom units are usually used for X-ray and UV visible region. Earlier people used to refer to the wavelength in angstroms, 4000 angstroms, 4030 angstroms, 4300 angstroms, like that, but nowadays we have replaced that with nanometer. So, millimicron is another one. Again it is a measure unit of wavelength, that is visible, that is in again millimicron is an older unit. Older unit means people used to refer to it as millimicron a few years back. That means, when you study old books, they would write like this, but what is essential to understand is millimicrons are essentially nanometers. Okay. Then there are units like microns and micrometer. These are defined like this, and then I have again it is a wavelength. Infrared, it is used in infrared spectroscopy, that is common in physics literature. That means, technical books in physics will refer to the infrared radiation in terms of micrometers. This is also popular among chemists. So, wave number, we use them, centimeters inverse, I have already told you, denoted by V bar, that is infrared as well as UV visible, but in UV visible it is less, sometimes in near infrared. Okay. Then you can use electron volts instead of wavelength, because in electron volts the notation is eV, but they are mostly used in X-ray and gamma rays. Then I can use simply frequency, that is radio frequency, and microwave. All of you must have heard that whenever you listen to FM radio or All India radio, this is such and such station giving you at 91.7 hertz, something like that, you would have heard, they are all in frequency. Similarly, cycles per second is also unit for radio frequency, that is rarely used nowadays. So, the interconversion of units I have tried to attempt here. So, it is only for you to remember Okay? And you can see nanometer can be converted into X-ray, infrared, X-ray, radio frequency, anything, all are interchangeable. Okay. So, I will not go more into detail, but this serves you as a guide for you to convert one energy level, one energy, one unit of one energy into another unit, that is it. So, it may be noted that regardless of the units of expression, any electromagnetic radiation of frequency will have unit wavelength and unique wavelength, any frequency will have unique wavelength and energy. Okay. So, the longer the wavelength, as I have explained to you earlier, lower is the energy and lower is the frequency. And energy is closely related to the temperature also. That is very important for us to remember, and that is expressed as E is proportional to Kb into T, where Kb is the Boltzmann constant given by 1.380 into 10 raised to 16 ergs per degree per atom, or 1.380 into 10 raised to minus 23 joules per kilo per atom. We will continue our discussion regarding the electromagnetic radiation a little more before we go on to the interaction. Thank you.